In this video, we will continue a discussion of quasi-linear utility function. Just to recap, quasi-linear function is a form of a function where one good appears in a nonlinear way and then other goods are captured by this bundle X. So here y is the nonlinear portion of the utility function and x is the linear portion of the utility function. So we have demonstrated that for this function, if a consumer wants to maximize utility in choosing x and y given the budget set, the Marshallian demand function for y is px over py, and the Marshallian demand function for x is I minus px over px. And then we've also seen that the compensated demand function for y is also equal to the Marshallian demand function, which is px over y. And this this equality is because there is no income effect. Now, in this video, we will show that the Slutsky equation holds for this case. In fact, we will use the elasticity version of the Slutsky equation, and we will demonstrate that for the good y. Essentially, that the income effect plus substitution effect equals the total price effect. But in elasticity form, this equation is written as the elasticity or the Marshallian demand elasticity of y equals the compensated demand elasticity of y minus the share of y in the spending times the income elasticity of demand of y. So this portion is the price effect, this second expression is substitution effect, and then this captures the income effect. Now right off the bat, we can see that because there is no income variable, and elasticity of demand with respect to income is defined as the percentage change of demand of y in response to percentage change in income, we can write this using calculus as the elasticity of demand with respect to income is y over I times del y over del I. Now because there is no y, no I in the demand for y, this expression is 0. So now we can look at the other elasticities and we can start working through them. The elasticity of demand y with respect to price of y is py over y times del y del py. Now what is y? We can now start plugging in the value of y here. Remember, y is given as px over py. So we plug this in here, and what we get is that the elasticity of demand of y with respect to y is simply py over px over py, then the partial of y, which is again px over py. Now here what we can simplify is we can bring this up, we get py squared in the numerator divided by px, and then the partial derivative of this with respect to py. This simply boils down to writing py squared over px times px. Now remember, we can pull px out because this is a constant when we're differentiating partially with respect to py, and the partial of 1 over py. And then the derivative of 1 over py with respect to, this should be py, will be the derivative of py to negative 1. So negative 1 is going to come out. Then we'll have py to negative 2, so which will be negative 1 over py squared. And we can see that what we get is py squared over px. The px's will get cancelled times minus 1 over py squared. So essentially these two terms get cancelled, and then we have py squared and py squared. They'll get cancelled. We'll be left with negative 1. So what we've established is that the Marshallian elasticity of demand of good y with respect to its own price is negative 1. Now all we need to do is find the elasticity of demand for the compensated function of y, and notice we can make use of this property again, that the compensated demand function for y is same as the Marshallian demand function. So the Marshallian demand function was px over py, which will also be the compensated demand function, and we've already established that the partial the elasticity of demand of this function with respect to price of y is nothing but negative 1. So what we have established is that the effect, which is the own elasticity of demand of Y with respect to the price of Y, equals the substitution effect, which is the elasticity of the compensated demand of Y with respect to the price of Y, minus the share of spending of Y times the income elasticity of demand of Y. This expression is 0, and minus 1 equals minus 1. So this proves the Slutsky equation in elasticity